Greetings and welcome. Today, with our introduction to calculus, we're talking about derivatives, which are going to be a function that represents the slope of another function at all points. All right, so we've briefly been talking about slopes of curves and the idea that if I wanted to find the slope of an awesome curve, say, at a particular point, I could do so, right? I could find a secant line, so I could find the slope of a line that passes through 2 points. But our goal is that what we're going to do is we're going to pick a point even close, that will get increasingly close to that, okay? So let's see. So here's our secant line. It's at those 2 points. All right. So if this is the point x comma f of x, we'll call it, right? X comma y. And this green point will be x plus h and f of x plus h. All right, so f of x plus h, what does that mean? It just means that point's y coordinate. All right? And we're going to move we're going to move this x plus h point closer and closer to the original point. So close, in fact, that we will take the limit as h approaches 0, so that there's no noticeable difference between those 2 points. And we're going to find the slope between those two things. And what is the slope formula? Over x2 minus x1. So if I wanted to find the slope between these 2 points, what I could do is I would just have, let's see, it would be f of x plus h minus f of x, right? Those are my y values. And if you wanted, you could label these points x1, y1, x2, y2. And then I'm going to subtract the x values down here. So this would be x plus h minus x, right? Which that, I think, simplifies a little bit. F of x plus h minus f of x. How does the denominator simplify there? H. What happened?
X.
Yeah, x minus x is just canceled out. So this is... Yeah. So this is the slope of a secant line. And we're going to find the slope of a secant line for values of h getting increasingly small, so small, in fact, that you can't see the secant line's difference between it and the tangent line. What? Can't see secant. What? Come on, guys. That was amazing. You're terribly disappointing. So anyways, what if I wanted to find the slope of the tangent line? Well, I'm going to take this equation, and the slope of the tangent line is just going to be the limit as h approaches 0 of this exact thing. F of x plus h, let's see, that plus sign looked sad, minus f of x over h. And this is the slope of a tangent line, and it turns out that, so that'll find the slope for a particular point. However, if I leave x defined generic, all right, just as being any value of x, we'll actually be able to find the derivative. So the derivative of a function is the following. All right, it's the function that is equal to the slope of any tangent line. All right, anywhere on the graph. So it's the x's are going to be defined in their generic mode. and the tangent or the derivative of a function. So it's written in a couple different ways. It'll be f prime of x. All right, so that's read as like the derivative of f of x. All right. Another way that it's denoted is dy over dx.
dy over the x.
dy over dx. And d is kind of like an abbreviation for delta. Delta is often a little triangle used to represent the change in y over the change in x, which is really what slope is. After all, it's the differences or the change in y over the change in x, dy dx. And I believe, wow, my mind just went super blank. All right. I believe both of these notations, I don't know if are you guys aware of the history of calculus? How it came about?
No.
It turns out Isaac Newton was a dude that Sir Isaac Newton, apparently. Man, I can't think of the other dude's name. Nah, he's some French guy. I don't remember. I feel ashamed as a mathematician not to remember his name. But nonetheless, all I can think of is Blaise Pascal, but I know it wasn't him, obviously. No, not de Moivre. Anyways. De Moiler. I'm just like combining mathematician names now. Well, anyways, in either case, it turned out two mathematicians in the same lifetime simultaneously discovered calculus.
Simultaneously
and independently. They both right? So each of these notations are kind of from each of their perspectives. One of them did it in terms of slopes, and the other guy did it backwards, like the reverse order, where he started with like tangent lines and then defined functions from that. And yeah, so it was just kind of like a really unusual, statistically improbable situation, right? Like what are the odds of two people independently discovering calculus at the same time? I guess it's kind of like wasn't like the invention of was it the light bulb? Similar sort of thing happened? Where someone just happened to get the patent before the other guy? Or was it... No, my bad. Telephone, I think. Anyways, whatever.
It was a radio.
Whatever. Anyways, Graham Bell, Benjamin Franklin, right? Leonardo da Vinci. Yeah, all these guys, they were all just like hanging out one day. Yeah, having a good time. They invented stuff. 1700s. Oh yeah, they were all over the place. But anyways... These are just two different notations. They mean the same thing.
He was the dude with the really?
Galileo?
Yeah, he was the dude with the telescope.
Yeah, sure. So this is the function, which is the limit of f of x plus h minus f of x over h. So this is the derivative. So today what we're going to try to do is find this derivative. So the derivative itself is a function. So that means if I plug in a value for x, if I plug in 0, it will tell me the slope of the original function when x was 0. If I plug in 7, the derivative will give me the slope of the original function when x was 7. All right? So interesting stuff is going to happen as a result. So let's actually do this for real.
Doesn't exist.
Yeah, these are all similar.
The line when h is equal to 0 does not exist. Because it isn't.
Right, if h was specifically, if I wasn't taking the limit, if h was specifically equal to 0, it would be, undefined because, it wouldn't work out. So, but we're all good. So let's say I wanted to find, the slope. That's not an instruction. Find the slope.
Just slope it.
Using the derivative. Using the derivative. So, and I guess I'll say at x equals 2 or something like that. And so let's say this is our original function. What if I've got f of x is equal to x squared minus 4x plus 2? So there's f of x. So now what we're going to do is plug it into this crazy thing. All right? That's what we're going to do. So f prime of x, or the derivative of f of x. Nope. What did I do, guys? Look what I did. I did f inverse. Shame on me.
No.
F prime of x. Also, by the way, there will eventually be f double prime, which is the second derivative. And that'll tell us even other stuff. But anyways, so f prime of x, or the derivative of x, is equal to, what was it? F of x plus h. So that means I'm going to plug in x plus h for all of these x locations, right? So that would be x plus h all squared minus 4 times x plus h plus 2. So this is f of x plus h. And then what am I doing? I'm subtracting f of x, right? So subtract, what's f of x? This whole thing. Minus x squared minus 4x plus 2.
Squared plus 2xh plus h squared minus
No, slow down, slow down.
4x.
All over,
Why are you subtracting
H.
that?
because I've got one y value minus the other y value. And I'm all over h. And oh, you know what I forgot? I forgot the limit, of course. Limit as h approaches 0. Silly me. Salami. So let's simplify this. Let's see what happens. So x plus h all squared is x squared plus 2xh plus h squared. All right?
Minus 4x.
Minus 4x minus 4h plus 2 minus x squared plus 4x minus 2 all over h. Right?
X squared negative x squared. Equals negative 4x, 4x.
Yeah, so this swipe, 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 and swipe, swipe. And what am I left with? I'm left with
2xh plus h squared.
h squared plus 2xh. I'm writing it in terms of h now. Minus 4h all over h.
Factor out an h.
Oh man, I still have limits all here, sorry. I'm a terrible person. Where's my limits at? Yeah, it looks like we could factor out an h here, right? I think I also... No, never mind. I was going to say, what if we divided everybody by h squared? But that technique only works when the limit is approaching infinity. Okay? So factor out an h. I'll get h times h plus 2x minus 4 all over h.
HH.
And then swing, swing. And I get, what is the limit as h approaches 0, 0 of this? H is approaching 0. 2x is approaching 2x. Because x isn't approaching 0, it's just the h was. And what's negative 4 approaching as h approaches 0?
Negative 4.
Negative 4. So that means what I've got is f prime of x is equal to 2x minus 4. Here's the derivative. So what does this function represent? It represents the slope at any point of the original function. Okay? Actually, if you want to go real crazy here,
Can you program a derivative?
yes. But I'm not going to even do that just yet. Let's see, what was our original function? It was x squared minus 4x plus 2. And so here's our original. And h, or g of x, which is my derivative in this case, we're saying is 2x minus 4. Let's see, display, line style, thick display, color. And I'll make it orange or something. So this orange function represents the slope of the purple function at any given point. Okay, so let me ask you this. When was this purple function's slope equal to 0? Well, that's the y value. It looks like over 2, down 2. So notice the slope was 0 at x equals 2. Notice this orange line. Where is the orange line equal to 0? At x equals 2. All right? When was the slope of this purple function negative? Anything less than 2, right? Right? This was decreasing. The monotonicity, right, was decreasing for values of x less than 2. When is the orange line negative? X is less than 2. So notice negative slopes all over here, negative values of the derivative all over here. And notice that the purple function was increasing for x greater than 2.
That's going to go to
So positive slopes and positive y values of the derivative also for x greater than 2.
Mr. White.
What's up?
The value of the purple line
Mm-hmm.
will approach negative infinity, and infinity, right?
What do you mean the value? The x value?
Well, the value of
The y value?
both.
Well, the y value is never going to go to negative infinity for the purple line. I mean, its range is negative greater than negative 2.
Well, it'll approach negative infinity.
I don't know what you're saying by that, I guess.
It'll approach the point negative infinity.
Yes, yeah. As x goes to negative infinity, that's going to positive infinity, yes. So the slope here is actually getting, as I go to the left, these slopes are increasingly steep in the negative direction, and that's what the orange line would represent, is that it's getting increasingly steep in the negative direction. And over here, it's getting steeper and steeper in the positive direction, right on this parabola, and that's exactly what this orange line is showing us. So that's what that represents. What did they want us to find out? What is the slope at x equals 2? Well, I could answer that by doing f prime of 2. 2 times 2 minus 4. 4 minus 4 is 0. So that means the slope at x equals 2 of f of x is 0. Which means if the tangent line has a slope of 0, that must mean that it was a critical point that occurred, maximum or minimum. And in this case, we could see by the graph that it was a minimum value. All right? So, interesting stuff going on. So the idea of doing this is you plug in x plus h for your function, subtract f of x, divide by h, take it to the limit, and then solve, and you can find your derivative. So what if I wanted to find out what is the slope of... Still got a couple minutes, guys. Slow down, slow down. What is the slope when x is 4 of the purple graph? So x equals 4 is right here. So that looks pretty steep. Pretty steep. How could I find out what that slope is? I could plug in 4 for the orange graph. It looks like it's actually going to be 4 is the steepness there as well. So I could do f prime of 4 is going to be 2 times 4 minus 4, is it? And I get 4 left over, so the slope is 4. Or what is the slope at 0? 2 times 0 minus 4, I get negative 4. And notice, does that make sense? Let's see, Geometry Sketchpad. At 0, it turns out that this point right here has a slope of negative 4 for the tangent line. All right, so it's just kind of weird that there's this graph that represents the slope of another graph at all points.
So, the slope of the parabola is the y value
Of the
one
derivative,
line at
yes.
that same x value.
You got it, 100%. The slope of the parabola is the y value of the orange, all right? The y value of the derivative is the slope of the original function. So that's the big idea. All right, good stuff. Let me shut this down.